I'm starting the video a little bit in the middle for some of this setup operation. But needing to put a main side collet into the headstock here. Nut cap for the dead length collet. Tightening tool, 3/8 hex drive. There. All the more tightening to do. Now I come over here to the air regulator and I shut off the pneumatic system. Now it'll be unpressurized. Now that the air has been killed to the machine, it's in emergency stop mode because of air pressure low. But that also means the pneumatic system can be done by hand and actuated. So my material bar stock is going to be 1/4 inch diameter. I put a gauge pin right there in the collet. And what I do is come over here to the headstock, the sliding headstock on the lathe, and I try to actuate it by hand. It's real stiff right now because I changed the collets, and the collets don't always have the same distance between the face and the taper. What I mean by that is this taper on the S25HM collet to here, that cone intersection, is a little bit different on each one. So therefore, it takes different amounts of force to actuate them. So that variation in every batch is why I just have to feel for the tension. Here's how I adjust that. Loosen these set screws, and then putting a spanner wrench right across the flats, holding the disc brake as I do it. It's in shut-off mode, emergency stop, power's been killed to the machine, but I'll be able to adjust it. Now that I'm done over here setting up the tension on the collet correctly, come back over to the collet and retract the quill inside. So just go in and jog, go into position so I can see easier. It's retracting, turn up the speed. But I just put a faint little red line down there, so when the carriage block goes behind it, then I say don't be in collet change mode. Real dangerous button to have activated at the wrong time, because that would allow a collision between the end of the collet and your guide bushing. So now I'll install the guide bushing. Now these hard-hinge lathes from this generation, really Tusagami, hard-hinge is a clone of a Tusagami, use an interesting guide bushing housing, much different than the modern machines of today. So, carbide line 1/4 inch one. Where's the label? There it is. Hard-hinge CD25. Goes right on the inside of it. And then you can see right over there is a 3mm hex. You rotate that, and this little pinion gear there spins these threads onto the end, and then it's what adjusts the tension from the front while you're using it, so that you can get the right sense of feel, so that it has a little bit of resistance as it goes forward. That's how it looks fully assembled. And now I drag it over to the machine. Oh, how it's retained in there is it has a little groove recessed in right there. When you tighten these 3 outer rings beside the slit, it presses these balls outward, expanding into that groove, holding in the whole guy bushing cartridge. I also have some work to do over here on the bar feeder. I was last running a different size of material, so the end of the push rod, I need to change out the feed fingers here that grabs the end of the bar or bar collet. So swing this out, and then I loosen these, and then these little pinching fingers right there that grab the end of the bar also need to adjust how wide or small they pinch on with the new diameter. Hard to film, so remove those and show the next step later. I've finished loading the bar of material. Now the guy bushing needs to be adjusted for its tension. So put it into spindle orient so that it has a lock on the orientation. Make sure that it's tightened down for the guy bushing cartridge. And now come over in here, make sure that the lock has been loosened, and now you have your pinion gear screw right in here. Tighten that down until I start to feel some tension. Just by feel, back it off a little bit, and then come back. Feels good enough. Light tension on material this small. Lock it down. Now that the material is loaded and ready, I need to face off the end of the bar to establish the Z0. Right now you can see it's far off from that. So in the program, I always have after the M30 end of program an N0 line for safe part off. Establishing the variables when you call up another macro to face off the end. So put it in auto, start it on the N0 line, and then let's look. Let's turn off the flood coolant. So then you can see that the headstock is repositioning. And now when we look at it, it leaves 25 thou on the face for later machining, which was one of the parameters in the macro. Call up, and it's ready. And it's done. Here's the program I'm using for turning the screw blank with the Swiss lathe. Copied from a standard template I use for most of these. Here's the profile of it with the speeds and feeds showing the geometry. 7.5 degree tip angle, go slightly past center line for it, come up, and then you can see over here the length 300 thou for the tip stick out. Turn in here to the pitch diameter, taper off of it, and then I call up here and prepare the parting tool. Over here now we have the weight code for the sub spindle side. Come up to 700 thou away. And then we do the parting operation once the sub spindle is positioned. And they're both synchronized in Z1, Z2 movements. And then once it's parted off, we round over the edge of it right in here, and then count it, retract, and then we get the parts catcher ready. Extend out the parts catcher, move forward a little bit so there's less of a gap, eject it. It has a little pneumatic ejector pin right on the inside of it. Retract it, and then we just come over here, and the macro would have been called that re-zeros the headstock, rechucking it so that it has enough stroke length for the next part to be done. That's essentially the program, and that's that N0 line I was mentioning earlier. So I use the Simco edit program because I can easily align the left path and the right path for these FANUC programs when on the Swiss lathe. Makes it very easy. Here's another reason that I like using Simco edit for writing these programs, is that it can backplot the toolpath. I just pasted it over in here to this other tab, and you can see how it rounds over the face, comes over in here, rounds off the corner so it's not a sharp edge, and all that can be easily troubleshooted and written, and it instantly updates the visualization. So that's what the program looks like. I can even double click a point and then it jumps down to that coordinate, jumps right down there. Very helpful for writing these quickly and troubleshooting them, since most of this geometry is fairly simple and doesn't need full CAM software. I have turned these blanks to just under the thread pitch diameter. Next, I put the hex drive with rotary broach, and then they get thread rolled. It's not as ideal, but I'm having to rotary broach these in the vertical mill because the lathe had an unexpected interference issue with how long this rotary broach tool holder was and how fat it was. It was causing interference with the sub spindle when it went to go grab the part. It was just about 3/4 of an inch too big with how fat this was. So there was just no room, and it's not ideal. So I'm just doing one at a time right now because this was an unexpected surprise. I should have planned ahead, but I'll make a fixture to do a few of these at one time. Right now it's only doing one. Not very efficient, but I need to make forward momentum while I wait for the proper tooling to be done. Here's the settings I'm using when doing the rotary broaching operation. It is perceived as a little bit slow because during this first run, I had it be a slower approach when it first came near the part. So you can see that it rapids to 50 thou above it, and then it goes and feeds close to it at about 5 thou per rev. And then once I'm 10 thou above the surface is when I start to engage the proper feed rate that they advise. And once I'm under the surface 20 thou, I speed it up to 600 RPM, go to the final depth of 1 times diameter, 94 thou, for 330 seconds, and then I retract slowly. All these steps, except for of course the slow approach coming above it, that's just so I don't shatter the rotary broach if I have a misload or anything else goes wrong, is all being called out by the speeds and feeds from Polygonal Solutions here in their pamphlet. And just starting slow with the first run, and then I'll find ways to take a few more risks and speed it up. Here's what the hex looks like now after being rotary broached. It fits in there quite nicely. But then the reason the hex is nice is because you can be putting this in your carburetor at an awkward angle using the ball pivot on the end of these wrenches. Here I am going to thread the screw, have it on the end of the Allen wrench here. Then here's the small thread rolling machine that I purchased for doing these types of tasks. A little small 3-ton machine from Tobest. Really happy with how heavy duty it is. I lifted off the cover for a moment to show how it works inside. These are on an eccentric sleeve right there, 0.75 millimeters. Eccentricity right now. Worm gear right there for power reduction. Over here I adjust the spacing between them for the pitch diameter, and over here got the oil pump, running straight oil. There's the workpiece support. Have a different carbide rest for every diameter, and the rollers also are different for every pitch diameter and thread count. Right now 832 is what I have in there. Interesting machine. Really helped out on projects like this. Looking at it with the optical comparator to make sure that the thread tip is the correct 7.5 degree per side angle, 15 degrees inclusive, and that it comes to the right tip diameter and corner radius there rounding over the edges. My client requested that I reference their name in the video for a little bit of advertising, I think. So if you need screws like this for your carburetor, here's the company.